Hi, my name is Elisa, an MPhil student in Statistics of CUHK. Thanks for your interest in our workshop about nonparametric regression. This pre-workshop video mainly talks about what is regression, why nonparametric regression is needed, and what will be covered in our hands-on workshop. So first, let's begin by a commonly asked question. What is a regression problem? Regression is used to find a relationship between an outcome variable y and one or some explanatory variable x. Let's start with one explanatory variable only, and you can see that regression is to learn the relationship between two things. Actually, regression is a very common topic, and we are faced with many regression problems in our lives. So for example, someone in the marketing management may want to know the relationship between the advertising investment and the monthly sales of one item. So to find a relationship, it is a regression problem. So here, we are interested in the question that how advertising will influence the sales. So advertising input as a factor of sales is the explanatory variable, and the outcome sales is naturally the outcome variable. So solving the relationship between them is useful because after knowing that, we will have a guidance to choose an optimal advertising input, which gives the maximum revenue. Another example in the agriculture can be like this. As we all know, plants' growth is closely related to the temperature. But what is the optimal temperature for the plant? We need to find the relationship between them. So again, to find the relationship is a regression problem. Temperature as a factor of growth is the explanatory variable, and then the plant growth is the outcome variable. So finally, let's move a little bit further to express the relationship by a mathematical function of the explanatory variable. So then, regression is the problem to learn an equation like this. Outcome variable y equals to a function of explanatory variable x plus some error. And our focus is just this function describing the relationship. Then, let's take linear function and polynomial function as two examples to discuss two types of relationship, which are linear relationship and polynomial relationship. So first, linear relationship, also the simplest relationship, can be expressed by a linear function. So for example, outcome y equals to 3 plus 0.8 times explanatory variable x. It means that as the value of x increase by 1 unit, the outcome y will increase by 0.8 units on average. So here, why we say on average? It is because that there are still some other factors that will affect the outcome y. The outcome y cannot be fully controlled by the explanatory variable x. And you may say from this plot, this linear relationship is shown by this right line here. And those gray dots may not exactly lie on this relationship line, but are roughly located around it. And this 0.8 average increase holds true for every possible 1 unit increase of x. So for instance, in our marketing example, if the relationship is like this, the monthly sales equals to 200 plus 0.5 times the advertising input. It means that each time we invest $1,000 more into advertising, the monthly sale will always increase by 500 units on average. Okay, but how come if the monthly sales do not always increase by the same amount on average? Then it is not a linear function, or it is not a linear relationship. And one possible answer could be they have a polynomial relationship. So again, here is a plot showing one polynomial relationship between the explanatory variable x and the outcome y. And it can be easily seen from the red curve here. As x increase by 1 unit, y will not always change by the same amount on average. And the temperature example can be a good demonstration of the polynomial relationship. So assume that there exists an optimal temperature at around 26 degrees centigrade that gives us the maximum growth of the plant. And the relationship between them can be expressed by a quadratic function like this. And we can easily find that when the temperature increases from 0 degrees to 1 degree, the plant growth will speed up. And when the temperature increases from 30 degrees to 31 degrees, the plant growth will actually slow down. So after talking about the linear relationship and polynomial relationship, it's time to discuss the corresponding regression problems. Okay, so first, let's recall this regression equation. So in the previous example, we directly give the concrete form of this function, like we use y equals to 3 plus 0.8 times x. So it's a linear function. But in reality, this kind of information is missing. So we do not know the exact relationship between the outcome variable and the explanatory variable. We even don't know whether this function is a linear function or a polynomial function or some other kind of functions. And then usually we will use a strategy like this. So we first plot the observed value of outcome y and explanatory x in a coordinate system like this. And then we try to guess which kind of relationship they have. So for example, here it looks that they follow a linear relationship. So we can express the problem by an equation like this. And then the next step is to find the most suitable value of parameter A and parameter B, which stand for the intercept and the slopes of the line. And our target is to make this line the one that describes the relationship between x and y the best. So to solve the value of parameter A and B, we need to do linear regression. Then, how to solve it? We have software to help us. We just need to throw those x values and y values into the computer, and the software, such as R, will help us to solve the value of A and B. Okay, so in another case, if we plot the observed value of x and y in a coordinate system and find that they may not follow a linear relationship, but a polynomial relationship. And then we need to express this relationship by a polynomial function with certain polynomial order. See, we use Q here. Again, we want to find the suitable value of those parameters beta 0, beta 1 to beta q. So to solve those parameters in this polynomial function, we need to do a polynomial regression. And similarly, software can help us. Okay, so up to now, you may find that the key step that determines which kind of regression will be used is to guess which kind of relationship they have. And then I will show your guess may be far from the truth and your eyes may fool you. So again, let's use the marketing example to illustrate. So there are some observed value of advertising input and the corresponding monthly sales, and we plot them in a coordinate system like this. And you may guess that they have a linear relationship, so you conduct a linear regression. And with the help of the software, we get the results like this. And we present our result by a blue line in the plot. It seems that this blue line captures the relationship well. But now, let me play the role of the god who actually generates those data and tell you the true relationship behind them is like this. So it is not a straight line, but actually a curly curve. As we invest more and more in advertising, the sales first go up quickly, but gradually slow down. So compare our linear regression result and the true relationship. It is obvious that our estimation is not good, especially for small value of x and large value of x. Okay, so then let's see what's going on in this plant example. So similarly, we plot the observed value of the plant growth and the corresponding temperature in a coordinate system. And it is clear that they do not follow a linear relationship, and we may consider using a quadratic function to model. So suppose your thought is the same as me, a quadratic regression is conducted. And we get a result like this, shown by the blue curve in the plot, and the gray dots lines around our estimate relationship. So it seems that we captured the relationship well. However, I will tell you the true relationship is like this. So again, we are far from the truth. So from the above two examples, we may have a deep feeling about how important a good guess is. So if a bad guess is made at the beginning, no doubt a bad result will be obtained. So how to lessen the risk of bad guess? The answer is very simple. Just guess less. And nonparametric regression is a method that has much less guess. So then the next question is, what is nonparametric regression? Okay, so let's first discuss the commonly used parametric regression, and later I will show you. Actually, nonparametric regression is even simpler than our familiar parametric regression. So far, we have talked about linear regression and polynomial regression. And actually, there are two examples of parametric regression. They are called parametric regression due to a very straightforward reason that both of them try to solve the parameter's value in the model equation. So for instance, in the previous marketing example, we use linear regression, and our target is to find the value of parameter A and parameter B in this kind of linear model. So similarly, in the plants example, a polynomial regression is conducted, and we try to find the value of parameter beta 0, beta 1, and beta 2 in this quadratic function. Okay. So many people like parametric regression because it includes many basic regression methods. And I think the first regression method to be taught in many regression courses will be the linear regression. Yes, admittedly, it is easy to understand and also easy to be implemented. Like just saying that what we need to find is just a line or a curve. But is it really as easy as what it looks like? My answer is no. So actually, parametric regression assumes a lot from the data. So for example, in our previous linear regression example, we assume that X and Y have certain linear relationship at the very beginning. That is, we limit the relationship to have one possibility only, which is linear with a fixed intercept value and also a fixed slope. What has not been mentioned is that we also need to assume the arrows follow a certain distribution, like a normal distribution. So in practice, it is very hard to check those assumptions. And once one of these assumptions is denied, a misleading result will be got. Moreover, data in the real world always do not have such a nice pattern. So just as what is shown in the previous examples, your guess may be wrong and sometimes saying is not the truth. Then let's see how nonparametric regression avoids making too much assumptions through a comparison of the key ideas of these two kinds of regression. Okay, so first, in parametric regression, as mentioned, it assumes that one model holds true for every possible value of its planetary variable X. Okay, so what does it mean? Recall the linear regression result we got in the marketing example. This kind of linear relationship holds true for either $0 advertising input or $1 million advertising input. On the contrary, nonparametric regression allows the model to change for different value of X. So we do not need to make a strong guess at the beginning. For example, we may only assume that for every small interval of X, there is a linear relationship between them. But the intercept and the slope of the line can be different. Okay, so we will use a marking example to illustrate this kind of idea. So we can clearly see that by allowing the model to be different for different value of X, the more rapid increase in sales at the first stage of advertising investment can be well captured. The slope of the fitting line when X is smaller than 100 is much larger than that for larger x. Okay, so in other words, the nonlinear relationship can still be captured by many linear models combined together. Moreover, those combined linear models also have the ability to capture different kinds of nonlinear relationships, including many complex relationships that even cannot be expressed by a single function. So finally, let's see what nonparametric regression can achieve without making a strong model assumption at the beginning, but let data speak itself. So if a nonparametric regression is conducted in this marketing example, the green curve shows the relationship we found, and it is nearly overlapping with the true relationship, which is shown by the right curve here. Okay, so compare it to the linear regression result we have got previously. It is obvious that this nonparametric regression performs much better. And similarly, in this plant example, we conduct the nonparametric regression and compare it to the polynomial regression result we got before. So we can see that an even greater improvement can be seen by using nonparametric regression method. So to sum up, in parametric regression, if a bad guess is made, a bad result is unavoidable. On the contrary, nonparametric regression guesses much less, but reasonable results can be got. And if the relationship to be estimated is complicated, nonparametric regression usually will give a much better result than parametric regression. So let's make less assumption and let data speak itself. Okay, so finally, in the coming workshop, we will discuss in more details on when nonparametric regression might be a better choice for analyzing your data. 4 different nonparametric regression techniques will be introduced and how they can be easily implemented in our software. Several hands-on practice with real-life dataset will also be discussed. Okay, so that's all I want to discuss in this video, and thanks a lot for your watching. Looking forward to see you in our workshop.